All right, so welcome to module number 14. Recall that in the last several modules, overall, we're discussing scientific programming, and we discussed how the, the amount of resources consumed by different algorithms scales, and computational complexity allows us to identify asymptotically the rate of growth of this scaling when it comes to computation. And there are also storage complexity and other similar notions. And having identified the type of scaling, we can use that to design algorithms. And in particular, we discussed briefly design and conquer algorithms. So what we're going to start talking about now is going to be some computational architectures where the emphasis will be going from simpler ones to more complicated parallel ones. And this is going to be followed in the next module, module 15, where we're going to be discussing parallel types of computation. So why are we interested in computational architecture? So recall that we started as a scientific programming material when we were discussing the computational complexity, and we made an assumption that we're running on a random access machine where each basic operation takes one instruction and takes a unit amount of time. And that instruction could be loading from something from memory, storing in memory. Recall in a Turing machine, we have a piece of tape moving forward and backward, and we're allowed to write and read and all that, of course. Other basic types of operations could be perhaps arithmetic, logic, if-then statements, and so on. So the random access machine is simple, but modern computational architectures, they offer very significant speedups if you start paying attention to the details. And one direction for speed up is using parallelization. And as we'll see in graphics units, you often have nowadays thousands of cores. So there's a significant potential for speed up, but we need to appreciate some of these opportunities, and it's advantageous to be aware of them. So there are different types of processors. On the low end, you have embedded processors that oftentimes in consumer products, let's say, you can think of a toaster or a laundry machine. There's going to be an embedded processor that it has a low clock speed, maybe a few megahertz, and the amount of memory is limited. This could be even a few kilobytes. The instruction set is going to be limited. You probably don't need too much functionality in a toaster, right? And that's because you're not trying to do much. And as a consequence of that, more sophisticated operations such as math, exponents, logs, stuff like that, special functions are not going to be supported in hardware, and instead they're going to require many clock cycles to emulate them in software. So that's on the low end. And then the typical CPU, or central processing unit, and here's a picture of an Intel server chip. You can think of examples, Intel, AMD, laptops and desktops, these types of servers. And nowadays, the smartphone chips that we have on more modern smartphones are starting to be very similar to laptop chips. And by laptop chips, I'm really trying to say low energy consumption, which extends the battery life. So in these CPUs, the clock speed is in the gigahertz range, in contrast to megahertz from before. The memory is now not kilobytes or hundreds of kilobytes, but gigabytes. It could be hundreds. Actually, in my research group, we have a server that's 5 years old by now, and it has 384 gigabytes. So by now, hundreds of gigabytes is, it's not something that you can buy at home for $800, but this is not unusual at all. And these processors, they offer fast mathematical operations that they're supported in the hardware. And of course, to implement this, you need many, many billions of transistors. So that's when we're talking about one processor, but what about multiple processors? Many computing systems support multiple processors, and Intel and AMD chips over the last decade or so, they have more and more cores. From what I recall, the recent higher end Intel consumer CPUs that they go by the i9 brand, I think that they have 8 cores, possibly even more. So for example, I have a desktop with an i7 with 6 cores, And until roughly 2 years ago, 6 cores would have been the absolute top of the Intel line. I mean, servers had more, but the absolute top uh, of the Intel personal line, and now 6 cores is becoming almost standard. So the trend has been toward more cores, and the reason for that trend is that if you increase the speed by increasing the clock speed, the clock frequency, you have a very significant increase in the energy consumption, okay? And on the other hand, running a slower clock speed, but in parallel, it allows you to overall consume a lower amount of energy. So as I said, maybe order of 10 processors is reasonable in 2020 on a higher end personal computer or a lower end server or medium end server. And then you have things that the number of processors there is much, much higher. And these are general purpose graphics processing units, GPUs. Initially, years ago, they were designed for graphics processing, but some years back, people realized that they're useful for scientific programming, especially if you need to run in parallel a lot of computational tasks that are basically almost identical except for the data flow. So these units are very highly parallelizable. They currently support up to many thousands of cores. And overall, if you can run things in parallel, the GPU is much, much faster, but it's constrained. And the reason is that it's not really fully parallel. You only have partial parallelization capabilities. Now, at the high end of the multiprocessor game, you have clusters, even cloud computing, where you can be sitting at home or even on the beach, and you can be logging into somebody's cluster. It could be, in NC State's case, we have a high performance cluster called HPC. You could also, let's say, log on to Amazon's AWS services or some other commercial service, and now you have access to thousands of computers, maybe even, maybe if you have a very fancy job a few years from now, maybe hundreds of thousands of computers. Now, part of the problem here is that we need to be processing data, and we need to store the data, and storage can be expensive. So here we have a concept called a memory hierarchy, which is represented in a pyramid. And toward the top of the pyramid, we have types of memory that are very fast, but that comes that comes at the cost of being basically expensive. And on the other hand, at the lower levels of the pyramid, we have bulk storage, which is much, much cheaper per unit of storage. However, it's much slower. So what we do, we partition the memory into a hierarchy, a pyramid, and we have different stages in our hierarchy. At the top of a pyramid, small amounts of memory, but very fast, and also very expensive per unit memory. But because we have a small amount, we're not spending too much on that. And at the bottom, we have memory that per unit of storage is cheap, and because of that, that allows us to have a lot of it, but it's slow. Now, the way how this becomes useful is that instead of spending, let's say, if you had the same amount of memory in different areas, different stages of this pyramid, different levels, if you had the same amount of memory, that would mean that the top is very, very expensive. So instead of that, we're putting less money at the top by reducing the amount of storage. And we're utilizing the property of memory locality that oftentimes when we run software, oftentimes we're looking for memory in the same place again and again and again, or perhaps not in the same place, but maybe at an adjacent address. And because of that, we can store in higher levels of the memory hierarchy that are fast. We can store the places that we've seen recently. And because we've seen them recently, they're likely to be seen again in the near future. And because they're stored in these higher levels, the CPU would be registers. The L1, L2, and L3 are cache memory. They're fast. You can access these recently seen things, which 90% of the time that's what you're going to do. You can access them quickly. And occasionally you'll need to spill to the main memory, which is somewhat slower, but very infrequently you'll need to go to the disk or even to the cloud and beyond. So what are the types of memory in this hierarchy? registers, they're on the CPU, there are several dozen of them typically, and we have same clock access. We can write, we can read, it takes no more than one clock. Cache. So as I said, there may be multiple levels of cache. Typically there are 3 in modern computers, and typically these would require, they would have several megabytes of memory, and the number of clocks could be from a small number of clocks to a few dozens of clocks. But pay attention that we're talking here about clock speeds of a gigahertz, and let's say 20 clocks is 20 nanoseconds. On the other hand, main memory or RAM, random access memory, typically instead of megabytes, you have gigabytes. And here the access would typically be many dozens of clocks, 100 clocks, maybe even a few hundred clocks. So whereas the cache might be up to 10, 20 nanoseconds, the main memory would be dozens of nanoseconds. And this is not a big deal, because remember that if we have, let's say, a 1020 megabyte cache in a modern processor, it means that 98% of the time, maybe even more than 98%, we get what we need from memory within 2-3 nanoseconds, and we're cool. And 1 or 2% of the time, we spend 50 nanoseconds. This is an acceptable penalty. And finally, if you spill beyond the main memory, which again is typically many gigabytes nowadays, the permanent memory, and permanent meaning that when you turn off the system, it'll still be there tomorrow. It could be in the disk on your computer, it could be cloud storage. That can be very large, many terabytes, but it's slow. If we're talking about disk, we're talking about on the order of milliseconds. And if we're talking about cloud, clearly this could take a while. What about GPUs? So as I said earlier, GPUs are parallel units that were initially designed for video processing, and people saw that they can be useful for some types of scientific programming. They typically have significant amounts of on-chip memory, significant meaning many gigabytes. And it depends whether on a personal level, you may be buying a laptop with a minimal GPU just for simple operations, and it may cost a few dozen dollars. At the medium level, you could get a GPU with 1,000 cores or a few thousand cores for $100, maybe a bit more. That's, let's say, for a person who's enthusiastic about playing video games. And then for the professionals that are working on these GPUs to run very intense scientific code, for them, this can run into thousands of dollars, okay? So you have potentially thousands of cores, and each of them has a small, fast local memory. And by small, I mean kilobytes, dozens of kilobytes. In the bigger picture of things, what we were discussing earlier, caches with many megabytes, that's not the situation here. So small local memory, but it's fast. And again, there's a memory hierarchy at play here that maybe not 99%, but hopefully 90% of the time, what you're looking for is right there. But the GPU chip also has significant slower memory. Again, it could be many gigabytes. And to put things in perspective, if I was saying that each core has a few kilobytes of local memory, and maybe there are a few thousand cores, we're talking about many megabytes, but not gigabytes. And at the level of gigabytes, the GPU does have slower memory, but it's not local, it's shared. So it could be, on the one hand, very slow for an individual core to access memory. And the solution is that the GPU designers, they've created hardware support for accessing adjacent locations in memory, where, let's say, location number 13 will go to core number 1, location number 14 to core number 2, location 15 to core number 3, and so on. And these things are very fast. And that allows you to access memory from the GPU's rather large non-local memory at a very high bandwidth, many hundreds of gigabytes per second, using a specially designed interconnect. So the bottom line is that GPUs are sophisticated beasts. They offer excellent computational performance, but to program them well, to exploit these opportunities requires a lot of sophistication. And GPU programming at a high level is an area that has a lot of demand. Okay, so that'll be it for module number 14 and module number 15 coming up.